Hello, in this lecture we'll answer on two questions. In the first question we'll find out the area of this semicircle that is inside quarter circle A or B. In the second question we'll find out the area of this green shape that is inside rectangle ABCD. So we start with the first question. So in the drawing we have a quarter circle. A or B is a quarter circle. We know that AO equals to 5 units in its length. That is to say, the radius of this quarter circle is equals to 5 units. And inside this quarter circle we have this semicircle, and our mission is to find out the area of this semicircle. So first of all, we will define the center of this semicircle. This point is point C. We will define the touching point of this semicircle with this quarter circle. This point is point F. Likewise, we will define the touching point of this semicircle with this quarter circle. This point is point G. We will define the point of tendency of tangent AO with this semicircle. This point is point L. And finally, we will define the point of tendency of tangent OB with this semicircle. This point is point H. In the next step, we will join points C and H together by straight line. CH, actually, line segment CS starts from point C, that is the center of the semicircle, and ends at point H, that is the point of the semicircle itself. So this is exactly the definition of a radius. So we will define the radius of this semicircle as x. Therefore CH equals to x. It is the radius of this semicircle. CF equals to CG. They are both the area of this semicircle. Therefore, each of those two line segments equals to x. CG equals to x. We join point C and L together by straight line. CL is of course also the radius of this quarter circle, that is equal to x. So here we have the radius CH of the semicircle is drawn to point H, that is the point of tendency of tangent BO with this semicircle. And whenever your radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius HC. If BO is perpendicular to HC, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CL of this semicircle is equal to x. The radius CL is drawn to point L, that is the point of tendency of tangent AO with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AO will be perpendicular to the radius LG. If AO is perpendicular to LG, it means that this angle equals to 90 degrees. and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we actually created the quadrilateral CLOH. Inside this quadrilateral CLOH, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral CLHO, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a tesseract angle if not a square. So we relate to this quadrilateral CLOH as a right angle because it has 4 right angles. But we also know that the opposite sides of a right angle are equal to each other. So an right angle CLOH, side CL must be equal to the opposite side OH. But CL is x, therefore OH must be also equal to x. Likewise, according to the sum rule, in the same right angle CLOH, side CH must be equal to the opposite side LO. But CH equals to x, therefore LO must be also equal to x. So actually found out that quadrilateral CLOH is not a rectangle but a square, while because of the fact that all of its sides are equal to each other, inside of this square equals to x. In the next step, we will join points O and C together by straight line. By joining points O and C, we get the right triangle CHO. The right triangle CHO is also an isosceles triangle because CH equals to HC. CH equals to HO. So, in the next step, I'll copy the right triangle CHO in a new page and we'll implement the Pythagoras theorem on this right triangle, triangle CHO. Repeat again, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle CHO that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CHO, CO square, that is the square of the hypotenuse, equals to CH square plus HO square. Again, CO square equals to CH square plus HO square. So I'll write it down. CO is the missing side, so we leave it as it is. So it is CO square equals to CH square. CH is x, therefore CH square is x square plus HO square. HO is also x, therefore HO square is x square. So in total, we actually found out that CO square equals to x square plus x square. X square plus x square is 2x square. So actually found out that CO square equals to 2x squared. Here we take a root out of this equation and finally get that the missing hypotenuse CO is equals to the square root of 2 times x units in its length. So here this is the missing line segment CO is equals to the square root of 2 times x units in its length. Here we know that point O is the center of this quarter circle, and from the center of this quarter circle, that is to say from point O, we have here line segment OC, and this line segment OC bisect chord GF. Why line segment OC bisect chord GF? Because GC equals to CF. GC equals to CF equals to X. So line segment OC that is drawn from the center of this quarter circle, that is to say from point O, bisect chord GF. And therefore we can implement here rule 7. So I'll read quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisect the chord, then the line segment will be perpendicular to that chord. So in the drawing we have a circle, and this is point O, that is the center of this circle. And we have also line segment OM that bisects chord AB. That is to say, AM equals to MB. And because of the fact that line segment OM bisects chord AB, line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule 7. So whenever you have a line segment that is drawn from the center of the circle, and it bisects a chord, then the line segment will be also perpendicular to that chord. Here, line segment OM bisects chord AB, and therefore line segment OM also perpendicular to chord AB. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule 7. So we can actually implement rule 7 in our drawing, because in our drawing, from the center of the quarter circle, that is to say from point O, we have line segment OC that bisects chord GF. And according to rule 7, line segment OC will be also perpendicular to GF. If OC is perpendicular to GF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 7. In the next step, we will join points O and F together by straight line. What is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and then at point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. And therefore, OF is the radius of this quarter circle, and we know that the radius of this quarter circle equals to 5, because AO is the radius of the quarter circle, that is equal to 5 according to what is given as the question. Therefore, OF is also the radius of this quarter circle, and therefore it is equal to 5 units in its length. So in the next step, I'll copy this right green triangle CFO in a new page, and we'll implement the Pythagoras theorem on this green right triangle CFO. Side CF equals to X, CO equals to the square root of 2 times X units in its length, and finally the hypotenuse FO equals to 5 units in its length. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right green triangle CFO that I copied from the original drawing. according to the Pythagoras theorem, in this right triangle CFO, FO square equals to CF square plus CO square. Again, FO square equals to CF square plus CO square. So write it down. FO square, that is the square of the hypotenuse, equals to CF square plus CO square. FO is 5, therefore FO square is 5 square, that is 25, and it is equals to CF square. CF is x, therefore CF square is x squared plus CO square. CO is equal to 2 times x, therefore CO squared is 2x squared. So in total, we should find out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So 25 equals to 3x squared. Here we divide this equation by 3, and finally we get that x squared equals to 25 over 3. So we found out that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. So what is the area of the semicircle? The area of the semicircle equals to the area of the circle over 2. The area of any circle is pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. And the area of the semicircle will be equal to pi times the radius of the circle squared divided by 2. The radius of this semicircle is x, therefore the area of the semicircle in total equals to pi times the radius square is x squared divided by 2. So the radius of the semicircle equals to pi x squared over 2. We have already found out that x squared equals to 25 over 3. So the area of the semicircle in total equals to pi over 2 times x squared. And x squared is 25 over 3. So we substitute x squared in this equation by 25 over 3. So in total the area of the semicircle equals to 25 pi over 2 times 3 is 6. So it is 25 pi over 6 square units. In terms of numbers, it is equal to 13.09 square units. Repeat again, we actually found out that the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, it is equal to 13.09 square units. So we finished with the first question. In the next step, I will present to you the second question and we will solve it. In the second question, our mission is to find out the area of this green shape. So in the drawing, we have rectangle ABCD. Inside this rectangle ABCD, we have this semicircle and this quarter circle. Again, our mission is to find out the area of this green shape. We also know that side AB of rectangle ABCD equals to 5 units in its length. And because of the fact that the opposite sides of a rectangle are equal to each other, we get that in rectangle ABCD, side AB equals to side DC, the opposite side DC. But AB is 5, therefore DC must be also equal to 5 units in its length. So I write it down. DC equals to 5 units in its length. In addition, we know that all the angles inside any rectangle are right angles. Therefore, this is angle ADC inside rectangle ABCD that equals to 90 degrees in its size. So this angle ADC equals to 90 degrees in its size. In the next step, we'll define the center of this semicircle. This point O, and we define the touching point of this semicircle with this quarter circle. This point is point S. So this semicircle has an external with this quarter circle. That is to say, they touch each other externally, this point S. And whenever you have an external notch between two circles or semicircles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing, you have those two circles, and they have an external notch between them at this point P. That is to say, they touch each other externally at this point P. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects their centers together is, of course, the straight line OM. And according to this rule 10, the straight line OM must pass for their touching point, that is actually point P. Again, the straight line OM must pass for point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally at this point S. And for that reason, we can implement here rule 10. The center of this semicircle is here at point O. The center of this quarter circle is here at point C. And the straight line that connects their centers together is, of course, the straight line OC. And according to rule 10, the straight line OC must pass for point S, that is their touching point. Again, the straight line OC must pass for their touching point, that is actually point S. Or OSC is one straight line. Again, OSC is one straight line according to rule 10. So I'll connect points O and C together by a straight line, and we know that the straight line OC must pass for point S, that is their touching point. According to rule 10, of course. So you can see here that the straight line OC passes for point S, that is their touching point. Or OSC is one straight line. If OSC is one straight line, it means that OC will be equal to OS plus SC. Again, OC must be equal to OS plus SC. So OC equals to OS plus SC. Why? Because of the fact that OSC is one straight line according to rule 10. So OC equals to OS. What is the definition of line segment OS? Line segment OS starts from point O, that is the center of this semicircle, and then at point S, this is a point on the semicircle itself. Therefore, this is exactly the definition of a radius. Therefore, OS is the radius of this semicircle. So we'll define the radius of this semicircle. Actually, we know that BC is the radius of the quarter circle. So we define the radius of this quarter circle BC as x. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. So AD equals to x unit in its term. AD is the diameter of this semicircle. So we know that the diameter of this semicircle, AD equals to x. If the diameter AD equals to x, it means that the radius must be equal to half of it. That is to say, it must be equal to x over 2. So the radius OA must be equal to x over 2, and the radius OD of this semicircle must be also equal to x over 2 units in its length. Okay, so OS is also the radius of this semicircle. We just write down found out that the radius of this semicircle equals to x over 2 units in its length. What is the definition? So OC equals to OS, that is x over 2, plus SC. What is the definition of line segment SC? Line segment SC starts from point C, that is the center of this quarter circle, and ends at point S, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, SC is the radius of this quarter circle, and according to our definition, the radius of this quarter circle equals to x. Therefore, SC equals to x. This is the radius of the quarter circle, that is equals to x according to our definition. So we actually found out that SC equals to x. So in total, OC equals to x over 2 plus x, that is actually equals to 1.5x, so 3 over 2x units in its length. So OC equals to 3 over 2 units, 3 over 2 times x units in its length. So here OC equals to 3 over 2 times x, 3 over 2 times x units in its length. In the next step, I'll copy the right triangle ODC in a new page, and we'll implement the Pythagoras theorem on this right triangle ODC. Here by PT is a relation for Pythagoras theorem. OD equals to x over 2 units in its length, DC equals to 5 units in its length, and just right now found out that the length of the hypotenuse OC equals to 3 over 2 times x units in its length. So actually, this is the right triangle ODC that I copied from the original drawing. Here by PT is the evaluation for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle ODC, OC square equals to OD square plus DC square. Again, OC square equals to OD square plus DC square. So I write it down. So all this OC square, that is the square of the hypotenuse, equals to OD square plus DC square. OC equals to 3 over 2 times x units in its length, therefore OC squared will be equal to 3 over 2 squared is 9 over 4 times x squared. So in total, OC squared equals to 9 over 4 times x squared. 9 over 4 times x squared, and it is equals to OD squared. OD is x over 2, therefore OD squared is x over 2 squared, that is actually x squared over 4, plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total we should find out that 9 quarters times x squared times 1 quarter x squared plus 25, or 9 quarters x squared equals to 1/4 x squared plus 25. Here we subtract x squared over 4 from this equation, and we get that 9/4 x squared minus 1/4 x squared equals to 8/4 x squared, and it is equals to 25. 8 over 4 is 2, so in total this expression equals to 2x squared equals to 25. Here we'll divide this equation by 2, and we get that x squared equals to 25 over 2. So here we take a root out of this equation, and finally we get that x equals to the square root of 25, that is 5, over square root of 2. So x equals to 5 over square root of 2 units in its length, and x squared equals to 25 over 2. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. So repeat again, we actually found out that the area of this green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So the area of the green shape equals to the area of rectangle ABCD. What is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. The length AB is 5, the width BC is x, therefore in total the area of rectangle ABCD equals to 5x. The area of rectangle ABCD equals to 5x minus the area of the semicircle. What is the area of the semicircle? The area of the semicircle equals to the area of the circle over 2. And the radius of this semicircle is x over 2. And therefore the area of the semicircle equals to pi times the radius of the circle squared divided by 2. So the area of the semicircle equals to pi times the radius of the semicircle squared. The radius of the semicircle is x over 2, so it is x over 2 squared divided by 2. So in total, the area of the semicircle equals to pi times x over 2 squared divided by 2. Minus the area of the quarter circle. What is the area of this quarter circle? The area of this quarter circle equals to the area of the circle over 4. And the radius of this circle, of the quarter circle, that is also the radius of the circle, is x. Therefore, the area of the circle is pi x squared. And therefore, the area of this quarter circle will be equal to pi x squared over 4. So in total, we shall find out the area of the quarter circle equals to pi x squared over 4. So the area of the green shape in total equals to 5x. Here we have minus pi x over 2 squared is x squared over 4 divided by 2. Minus pi x squared over 4. Pi x squared over 4. So the area of the green shape in total equals to 5x. Here we have minus pi x squared, and the denominator we have times 2 times 4, that is 8. So in total, the value of this expression is minus pi x squared over 8. Here we have minus x squared over 4. So here we will multiply both the numerator and the denominator of this expression by 2 in order to have a common factor with this expression. And we get that this expression will be equal to minus 2 pi x squared over 8. After we multiply both the numerator and the denominator by 2. So in total, the area of the green shape equals to 5x, and here we have minus pi x squared over 8 minus 2 pi x squared over 8. This actually equals to minus 3 pi x squared over 8. So in total, we actually found out that the area of the green shape equals to 5x minus 3 pi times x squared over 8. But we have already found out that x squared equals to 25 over 2, and x equals to 5 over square root of 2. So the area of the green shape in total equals to 5x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total, the area of the green shape equals to, here we have 5 times 5 is 25, so in total this expression will be equal to 25 over square root of 2 minus 3 pi over 8 times 25 over 2. So here we have minus 3 pi times 25 is minus 75 pi divided by 8 times 2 is 16. So in total, in the denominator we have 16. So we found out that in total the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. Or in terms of numbers, the value of this expression in total is equals to 2.95 square units. And that is the answer to the question. Repeat again, we actually found out that the area of this green shape equals to either 25 over square root of 2 minus 75 pi over 16 square units, or in terms of numbers, the area of this green shape equals to 2.95 square units. Okay, so in the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, we found out the area of this semicircle that is inside this quarter circle. So in the drawing, we have quarter circle AOB. Inside this quarter circle, we have this semicircle. We also know that AO equals to 5 units in its length. That is to say, the radius of this quarter circle is 5. Again, our mission is to find out the area of this semicircle. So first of all, we define the center of this semicircle, this point as point C. And we define the touching point of this quarter circle with this semicircle, this point as point F. Likewise, we define this touching point between this semicircle and this quarter circle, this point as point G. Likewise, we define the point of tendency of tangent BO with this semicircle, this point is point H. And finally, we define the point of tendency of tangent AO with this semicircle. This point is point L. Actually, we define the radius of this semicircle as x. Therefore, CF equals to CG. They are both the radii of this semicircle, so each of them is equals to x. In the next step, we join point C and L together by straight line. CH is also the radius of this semicircle, that is equal to x according to our definition. Likewise, we join point C and L together by straight line. CL is also the radius of this semicircle, is equal to x. So here we have the radius CH of this semicircle that is equals to x is drawn to point H, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius HC. If BO is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CL of this semicircle that is equal to x. The radius CL is drawn to point L, that is the point of tendency of tangent AD of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius CL. If AO is perpendicular to CL, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule 1. So by doing these constructions, we get the quadrilateral CLOH. Inside quadrilateral CLOH, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral CLOH we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral CLOH as rectangle because it has 4 right angles. So in rectangle CLOH, we know that the opposite sides of a rectangle are equal to each other. So in rectangle CLOH, side CL must be equal to the opposite side OH. But CL is x, therefore OH must be also equal to x. Likewise, according to the same rule, in the same rectangle CLOH, side CH must be equal to the opposite side LO. But CH is x, therefore LO must be also equal to x. So we found out that quadrilateral CLOH is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Its sides is equal to x. In the next step, we join points O and C together by a straight line. By joining points O and C, we get that here the right and associated triangle, triangle CHO. In the next step, I copy the right and associated triangle, triangle CHO in a new page, and we implemented the Pythagoras theorem on this right and associated triangle, triangle CHO. So this is the right and associated triangle, triangle CHO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So in this right triangle CHO, it means that CO square equals to CH square plus HO square. Again, CO square equals to CH square plus OH square. CO is the missing side, so we leave it as it is. So CO square equals to CH square. CH is x, therefore CH square is x square. Plus HO square. HO is x, therefore HO square is x square. So in total, CO square equals to x square plus x square, that is 2x square. So CO square equals to 2x square. Here we took a root out of this equation and finally found out that the missing hypotenuse CO is equals to the square root of 2 times x units in its length. Again, CO equals to the square root of 2 times x units in its length. This is 97 CO is equals to the square root of 2 times x units in its length. So here we know that point O is the center of the quarter circle. So from point O we have line segment OC that bisect chord GF. Again, line segment OC bisect chord GF. Why line segment OC bisect chord GF? Because of the fact that this GC equals to CF. each of those two sides equals to x. So I said OC bisect chord GF into two halves. And therefore we can implement here rule 7. So I repeat quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects a chord, then the line segment is perpendicular to that chord. So in the drawing we have a circle. We know that this is point O, that is the center of the circle, and we have also line segment OM that bisects chord AB. Again, line segment OM bisects chord AB, that is to say MA equals to MB. And because of the fact that line segment OM bisect chord AB, line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 7. So whenever you have a line segment that is drawn from the center of the circle and it bisects a chord, then it will be also perpendicular to that chord. Here, line segment OM that is drawn from point O, that is the center of the circle, that bisects chord AB, line segment OM is also perpendicular to AB. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we know that point O is the center of the quarter circle. So from the center of the quarter circle, that is to say from point O, we have line segment OC that bisects chord GF. Why? Because DC equals to CF. And because of the fact that line segment OC bisects chord GF, line segment OC is also perpendicular to GF. If OC is perpendicular to GF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 7. Okay? So in the next step, we join points O and F together by a straight line. What is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and then to point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle. We know that the radius of this quarter circle equals to 5, because AO, that is also the radius of the quarter circle, equals to 5. So OF equals to 5. So in the next step, I copied this right green triangle OCF in a new page, and we implemented the Pythagoras theorem on this right green triangle OCF. So actually, this is the right green triangle OCF that I got from the original drawing. CF equals to x. FO is the hypotenuse of this right triangle, CFO, that is 5, and CO equals to square root of 2 times x units in its length. According to the Pythagoras theorem, in this right triangle CFO, FO square equals to CF square plus CO square. Again, FO square equals to CF square plus CO square. So FO is 5, therefore FO square is 5 squared, that is 25, and it is equals to CF square. CF is x, therefore CF square is x square plus CO square. CO is square root of 2 times x, therefore CO square equals to the square root of 2 times x squared, that is actually 2x squared. So in total we actually found out that 25 equals to x squared plus 2x squared. X squared plus 2x squared equals to 3x squared. So in conclusion, we actually found out that 25 equals to 3x squared. Here we divided this equation by 3 and finally found out that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. And the area of this semicircle equals to the area of the circle over 2. The area of any circle equals to pi times the radius of the circle squared over 2. And the radius of this semicircle is x. And therefore, pi times the radius squared over 2 is pi x squared over 2. That is actually the area of the semicircle. But we just right now found out that x squared equals to 25 over 3. So we can substitute x squared in this equation by 25 over 3. We did it. We actually found out that the area of the semicircle equals to pi over 2 and x squared is 25 over 3. So in total, the area of the semicircle equals to 25 over 2 times 3, that is 6. So it is 25 pi over 6 square units. So actually found out the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, the area of this semicircle equals to 13.09 square units. Okay, so we finished with the first question. In the next step, I presented to you the second question, and we solved the second question. Our mission in this second question is to find out the area of this grand shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle we have this semicircle and this quarter circle, and they touch each other at this point. Point S is their touching point. Again, our mission is to find out the area of this grand shape. So first of all, we defined the radius of this quarter circle as x. So BC, that is the radius of this quarter circle, equals to x units in its length. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. So AD equals to x. But AD is also the diameter of this semicircle. So we know that the diameter of this semicircle equals to x. Therefore, the radius must be equal to half of it. So the radius of this semicircle equals to x over 2. So the radius OA equals to x over 2, and the radius OD of this semicircle equals to x over 2. Again, the opposite sides of the rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5. We also note that all the angles inside any rectangle are right angles. So this angle is one out of 4 angles of this rectangle ABCD, and therefore it is equal to 90 degrees in its size. So here we have an external match between this semicircle and this quarter circle. That is to say, they touch each other externally in this point, point S. And whenever you have an external match between two circles or semicircles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. So in the drawing we have two circles, and they have an external match between them at point P. That is to say, they touch each other externally at this point, point P. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects the centers together is, of course, the straight line OM. So this straight line OM must pass for the touching point, that is point P. Again, the straight line OM must pass for point P, that is the touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule, rule 10. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, we have an external match between this semicircle and this quarter circle. That is to say, they touch each other externally in this point, point S. And therefore, we can implement here rule 10. The center of this semicircle is here at point O. The center of this quarter circle is here at point C. And the straight line that connects the centers together is, of course, the straight line OC. And the straight line OC, according to rule 10, must pass for point S, that is the touching point. Again, the straight line OC, according to rule 10, must pass for point S, that is their touching point. Or OSC is one straight line. Again, according to rule 10, OSC is one straight line. If OSC is one straight line, it means that OC equals to OS plus SC. Again, OC equals to OS plus SC. OC equals to OS plus SC. So OC equals to OS. OS is the radius of this quarter circle, that is x over 2. And SC is the radius of this, again, OS is the radius of this semicircle, that is x over 2. And SC is the radius of this quarter circle, that is x. So OC equals to OS, that is x over 2, plus SC, that is x. So in total, OC equals to x over 2 plus x, that is 3 over 2x. So if you found out that the hypotenuse OC equals to 3 over 2 times x units in its length. So in the next step, I copied the right triangle ODC in a new page and we implemented the Pythagoras theorem on this right triangle ODC. So actually, this is the right triangle ODC that I copied from the original drawing. Again, the hypotenuse OC equals to 3 over 2 x units in its length, OD equals to x over 2 units, and DC equals to 5. So according to the Pythagoras theorem, in this right triangle ODC, OC squared equals to OD squared plus DC squared. Again, OC squared equals to OD squared plus DC squared. OC is square root of 2 times x, therefore OC squared is square root of 2 times x squared, that is actually 9 over 4 times x squared, plus OD squared. OD is x over 2, therefore OD squared is x over 2 squared, that is x squared over 4, plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total, we found out that 9 quarters times x squared equals to 1 quarter x squared, plus 25. Here we subtracted x squared over 4 from this equation and finally found out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared, and it is equals to 25. So 8 quarters x squared equals to 25. 8 over 4 is 2, so in total this expression equals to 2x squared, so 2x squared equals to 25. Here we divided this equation by 2 and finally found out that x squared equals to 25 over 2. So here we took a root out of this equation and found out that x equals to the square root of 25, that is 5 over square root of 2. So in total we found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawings it's very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Repeat again. The area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width of the rectangle. The length of this rectangle AB is 5, the width BC is x, so in total the area of rectangle ABCD equals to 5x. And again, the area of rectangle ABCD equals to 5x. Minus the area of the semicircle. The area of the semicircle equals to the area of the circle over 2. And the radius of the semicircle is x over 2. And therefore, the area of the circle is pi times x over 2 squared. And if we divide it by 2, we get the area of the semicircle. So the area of the semicircle equals to pi times r squared, and r is x over 2, therefore r squared is x over 2 squared divided by 2. So in total, the area of the semicircle equals to pi times x over 2 squared divided by 2. Minus the area of this quarter circle. The area of the quarter circle equals to the area of the circle over 2. And the radius of this circle is x. And therefore the area of the circle is pi x squared. And therefore the area of the quarter circle is pi x squared over 4. And again, the area of the quarter circle in total equals to pi x squared over 4. So the value of this expression is equal to the area of the green shape. So the area of the green shape in total equals to 5x, and here we have pi times x over 2 squared is x squared over 4 divided by 2. So in total this expression equals to pi times x squared over 4 divided by 2 minus the area of the quarter circle, that is pi x squared over 4. So in total the value of this expression is 5x, and here we have pi x squared, and 2 times 4 is 8. So in total this expression equals to pi x squared over 8. Here we have pi x squared minus pi x squared over 4. Here we multiplied both the numerator and the denominator of this expression by 2 in order to overcome factor of this expression. After we multiplied both the numerator and the denominator of this expression by 2, we get that this expression will be equal to minus 2 pi x squared over 8. Minus 2 pi x squared over 8. So in total, the area of the green shape equals to 5x minus pi x squared over 8 minus 2 pi x squared over 8. Minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total, the area of the green shape equals to 5x minus 3 pi x squared over 8. But we have already found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2. Therefore, 5x is 5 and x is 5 over square root of 2 minus 3 pi over 8 times x squared. And x squared is 25 over 2. So in total, the value of this expression will be equal to 3 pi over 8, and x squared is 25 over 2. So in total, we should find out the area of the green shape equals to 5 times 5 over square root of 2 minus 3 pi over 8 times 25 over 2. 5 times 5 is 25, so in total this expression equals to 25 over square root of 2 minus, here we have in the numerator 3 pi times 25, that is 75 pi, over 2 times 8, that is 16. So in total this expression equals to 75 pi over 16. So if I found out that the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units, and the value of this expression in terms of numbers, it is equals to 2.95 square units. Repeat again, I should find out that the area of this green shape equals to either 25 over square root of 2 minus 75 pi over 16 square units, or in terms of numbers, the area of this green shape equals to 2.95 square units. Okay, thank you very much.